All right, it's 11:15. I think we'll get started. So any questions or comments? Anything you want to chat about? Okay, so solutions for homework number 4 are posted. The practice exam is posted. And also I sent an announcement for extended office hours this week. And so make sure again that you get the settings on Canvas right to make sure you see the announcements in your email, because otherwise I think you have to go and check the class for the announcements. But I'm expecting that you're all getting that by email so we can make adjustments as needed. So if you didn't see any of that and you don't know what I'm talking about, go look at it this afternoon and then we can discuss. And of course, if you can't make office hours or if there's some conflict or something, you're always available to make an appointment with me. I need a little bit of a heads up. Sometimes I'm not available like right then or right the next hour. But since it's exam week, I want to make sure that you have enough time to ask questions and get the help you need and make sure we're good to go. The exam is going to be exactly like the first exam in terms of length, procedure. There's going to be a written part. I think there's 19 or 20 questions. And so everyone did a good job on the procedure for exam 1. And so I didn't see any major issues with Canvas not behaving or whatever. And so we're going to try exactly the same thing. And of course, I'm always willing to take feedback if something's not working, or if like 20 of you have an issue, then it's probably a big issue. And so, I'm happy to listen to that, but we'll try it the exact same way. And the exam is on Friday this time, not Wednesday. I wanted to give you a little bit more time. I know stuff was happening this last weekend. Still need to get back in the swing of things. And so the exam is on Friday. And you'll have the same amount of time roughly. So it'll be 70 minutes plus a reasonable time, 30 minutes for the written part. And you'll have from 8 a.m. until 11 p.m. The exam will be open. If you have a conflict, I just need to know beforehand. If you have an emergency that's an excused absence, just shoot me an email and say, I have an emergency, and we'll handle it later. But if you do have a conflict with something else that's not necessarily an excused absence, let's just deal with it. That's no problem, as long as I know ahead of time. Any questions, comments, anything people want to say? Yes? What's that? It's yeah. It is not only section 2 because you can't forget stuff like molecular weight, M0. You can't forget the difference between chain growth and step growth. So you need to remember some of the key. Can't forget TG or TM. Don't forget the basic comment or the basic concepts from section 1. But I'm not going to test you hardcore on section 1 stuff. 17 or 18 of the questions will be really focused on stuff we've covered in section 2, but you can't forget the basics. This is not a class where you can forget what M0 is because we haven't, talked about it formally. And so, like I said, there will be 1 or 2 things, 1 or 2 functional groups, or the difference between chain growth and step growth that you're going to have to remember, but you're not going to have to dig into Carruthers and all that stuff most likely. Yeah. And I do that because, of course, polymers is connected. I can't forget what molecular weight is, and I learned about it a long time ago. And so I want you to be able to integrate that knowledge across the semester, and that's why the final exam is comprehensive, and it will cover everything. And so don't forget stuff. Any other questions or comments? All right, we just are going to review tacticity today, and then we're going to introduce diene polymerization, and then you'll have everything you need to know for the exam. We're going to review Wednesday. We're going to talk about some questions, and then we'll be good to go. So what is the basic idea of tacticity? When you hear, does a polymer have tacticity or not? What are we talking about? In organic chemistry, what did you call it there? Chirality or stereochemistry, right? And for carbon, how many different substituents do you need on carbon in order to get a chiral carbon center? 4. And so that's key. In polymers, we count it a little bit differently. So you have to remember the different counting part in polymers, but you're looking for 4 different substituents. And we'll talk about monomers that can be chiral or not chiral. So I had a couple of good questions by email. And remember that isotactic is all the same stereochemistry as you go from carbon to carbon to carbon. You don't count the achiral carbons, right? Because these are not chiral at all because they have 2 different substituents on it. But you march down the polymer backbone chain, you figure out what the chiral carbons are based on 2 different attached substituents and 2 different pieces of the polymer. That makes the 4 substituents. And so you evaluate the chiral carbons as you go down the chain. And if they're all the same stereochemistry, exactly the same, it's isotactic. If they're alternating, exactly alternating stereochemistry, it's syndiotactic. If it's neither of those 2, for our purposes, it's atactic. So it could be a pattern. There could be 1, 2 stereochemistry the same, the third one is different, then 1, 2 the same, and the third one is different. That is atactic in this class because it's not perfectly alternating and it's not perfectly the same. So we're not going to deal with mixed tacticities in this class. We want to learn the basics. And so even though you might convince yourself that there's some pattern, if it's not isotactic or not syndiotactic, it is atactic. Those are the only 3 choices. Or tacticity might not be possible, and we'll talk about that case in a second. Is there a hand? Yeah.
So like if we have a very, very long polymer and one of them is different, is that still just considered atactic?
Yep, in this class it is. If it's not, perfect. Now, in reality, people will say this polymer is 95% isotactic or 98% syndiotactic. So you'll see a percent tacticity, which means for a polymer chain that's got a degree of polymerization of like 1,000 or 500, that means there are long runs of isotactic or syndiotactic. But we're generally going to look at diagrams like this. And so you're not going to have to evaluate 100 carbons. You're going to have to evaluate like 6 or 7 and tell me what the tacticity is based on that. Yes?
So what is the effect of tacticity on?
We're going to talk about that in a sec. Good question. I will answer it coming up. Any other questions? Yes?
It's like 2, 2, 2. Does that still count as syndiotactic, or does that make every other?
2. So, but go ahead and say that question again.
Like if you have syndiotactic is alternating, like one's this way, one's the other way, one's this way, one's the other. What if you had like 2 one way, 2 the other way, 2 one?
That's atactic. Yeah, that would be very cool. The issue is that it's really hard to make those pattern tacticity polymers. It turns out that polymer technology has evolved where it's easier to get all the same isotactic. There's actually catalysts that do syndiotactic. It's good at alternating, but the way that these polymers are made, it's really hard to get that pattern tacticity. So it's not common at all. It doesn't have a special name for us. We're going to call it atactic. Yeah.
So for each of the actual chiral carbons, can we consider them all chiral centered or something like that, or should we consider them not chiral centered?
These carbons with 4 different substituents, that's chiral, that's chiral, that's chiral, that's chiral. So a stereocenter is chiral by definition, but it has to have 4 different substituents. So you notice these carbons with 2 hydrogens on them, the tail, right? Because there's 2 hydrogens on there, this is not chiral, or it's achiral, which means it has no chance of having tacticity at all because it only has 3 different substituents, 1 chain end, the other chain end, and then 2 hydrogens that are the same. So if it's chiral, or if it's a potential, or if it's a stereocenter, it has to have 4 different substituents. If it only has 3 different substituents, which carbon in polymers has to have because the 2 chain ends are automatic, right? And so you've got 2 chlorines here, or 2 fluorines, or 2 hydrogens. it will be a chiral. You can't assign it stereochemistry. All right. And so the way that we evaluate these, now that we're all set, and let's switch over to this. Press the right button. So we talked about this problem, and this is not a clicker question yet. We're going to have plenty of clicker questions. But I asked you, what was the tacticity of this polymer? And so in general, we're going to draw the backbone, these thin lines, in what's called a planar zigzag conformation. So here is my molecular model. And you notice that the carbons are these little gray knots right here. There's a carbon, 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 carbon. And they all lie in one plane. So if I hold up a sheet of paper, which I don't have, if I hold up my phone, you can see that all those carbons lie in the plane of my phone. And those are the thin line zigzags that are drawn on the board. So that's the backbone in this planar zigzag. These white balls are two hydrogens, and the red and green balls are two different substituents on the head carbon. So we have one side of the polymer chain with the pink thing on it, that's 3. This other side, that's substituent 4. So this is a chiral center. Now notice, I can turn this chiral center. I haven't changed any bonds. Haven't done any chemistry, right? No changing of bonds. And now I've got the 4 carbons in the plane of my phone again, right? So I just changed the conformation from, let's say, all trans, because everything is in transplanar zigzag configuration. And since it's a single carbon bond, I can change it to cis, because these carbons are on the same side, but they're all in the same plane. And notice when I do that, in cis configuration, the red ball is pointing out at you all. Can't see that, you can come up here after class and check that out. When I put it in trans, I haven't done any chemistry, the blue ball is pointing out at you now, and the red ball is facing away. And so that's why we talk about, when we analyze the conformation of these polymers, we have to get the substituents on one side of the polymer chain, or all facing up, or in some orientation where we can evaluate how things are arranged in space. And so key to this is, if we have one methyl group here sticking out of the board, if I can draw on this, this methyl group is sticking out on the board, and it's hard to evaluate the different stereochemistry around these carbons. But if I rotate this carbon back and I get my dashed arrow, because it's going back into the board, now I've got 2 different stereocenters here that I can evaluate, and this is syndiotactic. So if I drew this correctly, of course, this is in cis configuration. Let me go back to black. This is in cis. No bonds have been broken. This is in trans. But in order to evaluate the stereochemistry, I'm allowed to rotate the molecule if it's single carbon bonds, right? If it's a double bond or something, I can't rotate it. It's stuck because we don't have free rotation around double bonds. But this is the key to evaluating stereochemistry, that you need to have the substituents on the same side of the chain on paper. And you need to keep track of what's pointing out at you versus what's pointing back into the page. Yes?
So because one's pointing out on the page, one's pointing into you, does that mean, is that why it's symbiotic?
That's right. So you notice that what haven't I drawn on this chemical structure? What's missing? Hydrogens, right? So that means I've got a hydrogen. Well, let me not do it like that. You know, if that one's pointing out, I've got a hydrogen pointing in. And so when I rotate that methyl group, it's going to get crowded, but you know, so I've got the same thing over here. Let me just draw it down here, even though that's not perfect. That carbon doesn't change at all, right? It's still got a hydrogen pointing in, but since I rotated the methyl group behind the plane, that means my hydrogen, geez. my hydrogen is now coming out. So you can draw it in this orientation where you get both substituents sort of on the same side, or you just have to develop a notation where you keep track of what's going in and what's going out of the plane. So this shows one example is so I can take the isotactic and I can rotate the substituents. I can do all sorts of things, and the tacticity doesn't change when I change the conformations. Same with this. I didn't make any bonds or break any bonds. I just rotated one of the substituents back into the plane so I could evaluate what the tacticity was in comparison to each other, and I'm able to get that problem. And this is worth practicing. It's worth trying to see, okay, I'm going to rotate this carbon. One substituent's going to go into the plane, one substituent's coming out. Yes?
So if you didn't rotate, would it stay isotactic?
No, this polymer, once it's syndiotactic, it is always syndiotactic. You cannot change it. So because in order to change the chirality of a carbon, you have to make and break bonds, right? So once I synthesize the polymer, once I show you this polymer, this thing is always syndiotactic. Always, no matter what conformation. So as soon as I draw it, it is the chirality it is. So you can't take this isotactic polymer on this slide and change it into a syndiotactic polymer. That doesn't happen. You can rotate all the bonds. You can keep track of where the substituents are going into and out of the plane. But this isotactic polymer is always isotactic, no matter what the conformation is. Same with the syndiotactic. So you don't change the tacticity by rotating. Or you can't change the tacticity by rotating bonds. So you need to know sort of the signatures of tacticity, but also you need to do this rotation, and that's something you should look in the book for. There will be some practice problems on that. I think there's a practice problem on the exam, so you can sort of get that. Yes.
So the two CH3s that are next to each other, would that be like an XX or the YY?
Yeah, this is a little bit of a funny polymer because it's a monomer that looks like this, right? If we decompose this, this is CH3H, and this guy is CH3H. We don't see a lot of monomers like that. They actually don't polymerize very well. But in this example, we have what we have, and we'll have 4 different substituents. 1, 2, polymer this way, 3, polymer that way is 4. And so both the carbons in this case are chiral. And the rule is we look at the chiral carbons and figure out what their stereochemistry is in relation to each other. So if we had 5 achiral carbons and a chiral carbon, another 5 achiral carbons and a chiral carbon, another 5 carbons, chiral, we would evaluate the order of those chiral centers to assign it a tacticity. Yes.
Maybe just a question. I'm confused why exactly we're saying this in syndiotactic.
Because it's alternating stereochemistry. So remember, alternating, because one substituent is coming out at you, that sets one stereochemistry, and then if you step over to the next one, that same substituent is going back. So the stereochemistry has to be opposite. Remember, it's hard to see right here, but in this case, all the Y's are coming out at you, right? Every single Y is coming out of the board. That's isotactic. And then if you look here, the Y's alternate into out of the board, into out of the board. That's alternation, which is syndiotactic. And so since these are alternating, that's syndiotactic. Yes.
Do you always have to rotate the polymer that's given, like the monomer in this case, or is that just this case that you have to rotate?
You need to rotate to get the substituents on the, well, I don't want to use red. On the same side of the chain. So the key is to get all of the key substituents, the ones that are the same, on the same side of the chain, so you can evaluate that stereochemistry. So these are drawn a little bit differently here than this one is, but notice we rotated this so all the XY substituents, sorry, the slide's getting messy, but you'll get my drift. All the XY substituents are on the same side of the chain, all the hydrogens are on the other side of the chain, and that allows us to visually inspect the stereochemistry rather than, you know, sometimes in organic chemistry, you're trying to figure out if something was chiral and it's hard to see it in 3 dimensions. This is a shortcut in polymers to try and evaluate that stereochemistry. And stereochemistry is not substituents on the same side of the chain, substituents on different sides of the chain, because, you know, when I have a real polymer and I'm rotating this thing, there is no side of a chain if I just have a polymer out there in space. But we represent the nomenclature like this because then it's really easy to see chiral center to chiral center, are they the same or not? So I want you to practice using stereochemistry, tacticity, all the same stereochemistry, alternating stereochemistry. It's not same side of the chain or other side of the chain. That doesn't have any bearing once we talk about real polymers. This is just a shorthand nomenclature where it's really easy to evaluate by eye rather than, you know, even when I see this thing, this polymer right here, you know, I've got a really hard time deciding what the chirality is at this carbon versus this carbon. You know, so unless you really get in there and figure out what's going on, that's really difficult. But if I get all my substituents lined up, it's really easy to interpret this. And since one methyl group is going back, and on the next chiral carbon, the methyl group is coming forward, they've got alternating stereochemistry, so they are symbiotic. Yes.
So if we were to make this like send the actual chain of it, the next methyl group would actually be the one going into page 1 would be X out.
Yeah, so we can keep this up. That's a good question. So if we insert a new slide and let's just let's take this answer. I don't know if I can grab this. Oh, I can. So this thing is symbiotic. If I wanted to draw another symbiotic monomer unit, here's 2 more carbons. Wait, 1, 2. Let me get rid of this. 1 carbon there, 1 carbon there. So if I wanted to keep going with symbiotic, I would have to have a methyl group, and it's easy to draw it like this. Let's just put another parentheses there just because. Going back out, or sorry, going back into the page. And then coming back out. And of course, I always have my hydrogens on the opposite, even if I draw them in this orientation, I know that the hydrogens are alternating with the methyl groups because they have to, because all these carbons are sp3, right? So I can draw it like this. It's a little bit crowded. It's a little bit cramped. But you notice that all these carbons now, this stereocenter, this stereocenter, this stereocenter, and this stereocenter, there's no extra carbons in there, right? There I didn't introduce any chemistry. I just kept alternating methyl groups coming out of the board, methyl groups going into the board on each carbon. So I kept up that pattern. This polymer is all symbiotic. Yes.
No, we make the one going into the board X and the other one going out of the board Y. When that just essentially means that's going to be X, because if you have the one going into the board X, Y, X, Y, X, Y, it's going to have the same pattern regarding the actual structure. Not.
Well, so you could make the methyl group X, right? You could make all these X's if you wanted. X, 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 and you could make all of these Y, 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 Y. Remember, X and Y are on the same carbon in these diagrams. It's the same carbon This just looks a little bit different than this diagram. But this is still, X is alternating, right? Yes.
It doesn't have to be like 2 in a row. It can be like.
It doesn't have to be 2 in a row. So for polystyrene, there's such thing as syndiotactic polystyrene, right? And that looks like this. So here's one monomer unit, or here's another one of polystyrene. Let's just draw 2, right? On the other, this is H. Let's just do it like this. Doesn't matter what these H's are, right? Because I could draw these H's however I want, or these protons, but there's no chiral carbon. So I don't even have to evaluate those carbons. So these aren't chiral. And so I'm going to put my substituents on the same side of the chain. Oh, wow, geez. So if I do a fat arrow here, I have my benzene ring, and then I do my proton. And let's do a fat arrow here, attached to my benzene ring. And then I have my proton, right? This is 2 repeat units of polystyrene. Is this isotactic, atactic, or syndiotactic? Yes. Iso. Why is it isotactic?
Because the groups are all oriented the same way.
Yeah, the stereo centers have the same chirality. That's the scientific words. But yeah, all the groups are oriented the same way, or the 2 stereocarbons have the same stereochemistry because they both have styrenes coming out at you. That's a substituent that we care about. Both protons going back. And so if you assign X and Y's to this, it looks like isotactic polymer. So don't get caught up when there is no tacticity. You really don't want to think about what's going on here, because you know there's not 4 substituents on those carbons. And so they're not tactic at all. So there is no tacticity. So you can't assign those. You really want to spend your time thinking about what's going on with the chiral centers. And this is isotactic. And so you could write down syndiotactic if you wanted to. For practice, you say, well, if that is isotactic, why don't I just change one thing here? That's a fat arrow. There's my benzene ring. Now this is syndiotactic because I changed the stereochemistry. I didn't rotate. I didn't do anything. I actually changed the bonds in order to get different stereochemistry, different tacticity. This is worth practicing. You know, it's worth trying to figure this out. Although even with the 3D model, it's a little bit hard to see. What I would do is I would practice this slide. I'd practice this slide, practice this slide, practice drawing those structures so you know how to get it right. And the easiest thing to do is that perhaps, you know, it's hard to draw polystyrene in stereochemical configuration straight up. And so at first you just say, okay, what is polystyrene to start with? Or polyvinyl chloride. Remember, this monomer is this. This monomer is this. So make sure you can get the repeat units right. Make sure that you know that there's a hydrogens here on those things. And then you can start to think about, okay, now that I've got all the bonds in the right place, where do the styrene rings need to go to get the stereochemistry that I'm looking for? And so you can go erase some bonds and put it in the right stereochemical configuration. So it's really hard to draw styrene right away when you're trying to get the fat arrows and the skinny arrows, or the fat arrows and the dashed arrows right. It's easier if you say, okay, I've got the skeleton right. You know, I've got 1 carbon here, got 1 carbon here. I've got 2 carbons in my repeat unit. That's good. This is going to be my nominal repeat unit. So that all checks out. Now, what do I need to do with the stereochemistry? Yes.
actually never mind.
You cool? Yeah. It's tricky. I mean, you know, it was hard figuring out esters, amides, functional groups, all that stuff from section 1, right? This is one of the tricky chemistry parts of section 2, because these monomers, you know, you should be pretty familiar with how to do polymerization, initiation, and termination with these chain growth monomers, but the stereochemistry does add a wrinkle. Can step growth polymers have tacticity? We're talking about chain growth here, right? They're easier to draw. Can you get tacticity in step growth polymers based on your knowledge? It turns out that you can, you just need to build in chiral carbons in those polymers. So there's lots of step growth polymers out there that we can draw upon, but you could put a chiral carbon in the middle of a chain somewhere and you will have a chiral center that you can evaluate. So it's not as common because the synthesis is different, but you can have chiral step growth and chain growth polymers. You just need to evaluate the stereochemistry just like we've done. Any questions? All right, this is worth looking at, studying, asking questions in office hours or review on Wednesday. All right, so the way that we use this is we talk about properties. Why does chirality matter, right? Or why does tacticity matter? So you can get out your clickers. And we're in C and D, and I will update clickers probably on exam day because I'll have a little extra time. So we'll make sure everyone's registered by the end of this week. So which form of polypropylene would be more crystalline? I haven't asked you a question like this before. We haven't talked about it, but what does atactic sort of mean to you in terms of the order of the chain? It's a little disordered, right? Because it's got different stereochemistry. And so you've, well, most of you have taken MATSE 201. And in order to get a crystal, or when we think about a crystal, what do we really need in a crystal? Regular stuff that's organized. We need good structures. Everything needs to pack together. And so the question is, based on what you know about these types of tacticity, which one do you think is more regular, which would lead to more order in the crystal? And I'll go ahead and ring in. And of course, isotactic is a more regular chain. If all the stereochemistry is the same on every single carbon, remember there's a hydrogen, well, let me just draw it. You know, there's 2 hydrogens there, so we don't need to care about the orientation. If we want to make this isotactic, since it's polypropylene, that's polypropylene right there. This is isotactic now. I mean, there's only one tacticity. And so we know that it's repeated exactly the same every single time. And so that's how we turn that polymer into isotactic. You can't turn it into syndiotactic without drawing 2 monomer units, right? Because you need to get the alternation. It's hard to know what the next monomer unit is, except if they're all the same with this parentheses on it. This is isotactic and it's more crystalline. Yes?
So what would be more crystalline? Stereotactic or syndiotactic or isotactic?
Yeah, so that's a good question. Is syndiotactic more crystalline or isotactic? They're both regular, right? One is just regular all the same, and one is regular alternating. Which one is more crystalline? Yes?
It would be iso.
So in general, it's iso, but this is material science, so there's always exceptions. So I'm sure we could go look up the crystallinity of some different polymers, and based on exactly what the unit cell is, sometimes having the functional groups alternating stereochemistry gives you higher crystal energy, which would lead to higher percent crystallinity. But in general, isotactic is more regular and more crystalline. I probably won't ask you that question for points, but I will ask you something like this for sure. All right, you can keep your clickers up. Well, I can stop the clicker question. All right, we already got that. Oh, I have more clicker questions coming. So in order to control stereochemistry, we've talked a lot about stereochemistry. We do this very interesting type of polymerization called coordination polymerization. So this is a vocab word that you should know. Right now, what types of polymerizations have we talked about so far in section 2? So in addition polymers or in chain growth polymers, what are sort of the classes of polymerization that we've talked about? Free radical or radicals just fine. What else? Cationic, anionic. What's the special form of anionic? Living anionic. And so coordination is a type of polymerization based on how the chemistry is done. It's actually a type of catalyst, or it can be a type of catalyst. And two people back in the day, two scientists came up with this type of catalyst, and it's called Ziegler-Natta polymerization, and they won a Nobel Prize for this, Carl Ziegler and Julio Natta. Okay, but coordination polymerization is another type of polymerization to make addition polymers, just like free radical, anionic, cationic. Now, you don't need to memorize this, but this is why it's called a coordination catalyst. So the catalyst coordinates with the double bond, and that allows the stereochemistry to be the same or to be alternating in all the monomer units. So the catalyst actually controls the stereochemistry. So if you go get your PhD from Bob Grubbs, who's at Caltech, who's another Nobel Prize winner in coordination catalysis of polymers, because he came up with a very special type of catalyst called a metathesis catalyst. If you go work for him, you'll study how to design these catalysts to get them to give you alternating stereochemistry, or to get them how to give you the same stereochemistry at each stereocenter. This is how modern polyolefins are made. Polypropylene is made with a lot of these types of catalysts. They use a lot of metathesis catalysts to make designer polyolefins. Good enough for this class, knowing that coordination polymerization controls stereochemistry, and there's something interesting going on with the catalyst, that's good enough. So you don't need to know this chemistry, you just need to know that it's coordination polymerization for this class that gives you stereochemistry control. You don't have stereochemistry, stereochemical control in free radical, you don't have it in anionic, you don't have it in cationic unless you do something really special, but you do have it in coordination catalysis. And that's why there's been multiple Nobel Prizes for this sort of polymer technology. It's been really important to the field. Okay, any questions on that? I will just stress that you should know this vocab word. And as far as we know in this class, coordination polymerization is the only way you can control the stereochemistry. All right, questions, comments? All right, the very last thing you need to know for the exam is addition of dienes. So it's addition polymerization. We haven't changed the mechanism. There's nothing special here. But what's special is that dienes contain two alkenes in one molecule. And for our purposes, those dienes are going to be in conjugation with one another. So if you look at just a simple diene, and let me just add a new slide here. Butadiene is our simplest diene that we'll talk about. How many carbons are in butadiene? 4. 1, 2, 3, 4. You can put in all the hydrogens if you want. And so what if I'm going to do free radical with this thing, right? I've got my initiator there. So I have a radical that could be a growing chain end. It could be whatever it is. And so for free radical, remember, I only need one electron to make that covalent bond. And so this electron has nowhere to go. It's going to sit either on carbon number 2, or if I combine it with an electron from the conjugated double bond, then I can kick off another electron. Notice I get, whoops. I can get my eraser back. Covalent bond to carbon number 1. Now, between carbon 1 and 2, do I have a double bond or a single bond between carbon 1 and 2? Single, because I took a half arrow one way and a half arrow the other way. So I only have a single bond. Here's carbon number 3. What did I do to the bond between carbon 2 and 3? It's a double bond because I shoved 2 electrons in there. That's what my half arrow is saying. Just trust me, those are half arrows. You can practice it. And then the bond between 3 and 4, is that a single bond or double bond? Single bond, right. And then of course I have my half bond. And so I'm going to have a parentheses there, and eventually I'm going to make a polymer that looks like that. I still have 4 carbons in my repeat unit. I haven't lost any carbons, right? This is not condensation polymerization. I haven't lost any hydrogens. I've just moved half arrows. And so now I go from a monomer that's butadiene to polybutadiene. We call it polybutadiene, even though it's got 1 double bond. It's actually not a diene. It's 1 double bond between carbons 2 and 3. Because I have to put those electrons somewhere, right? I can't put radicals on carbon 2 and carbon 3 because radicals can't live close together. And we don't make any polymers in this class with radicals just sitting there if they're not the growing chain end. Yes?
So this doesn't make a cross-link thing because they're just so close together, correct?
That's right. This does not make a cross-linked polymer. And this is the one exception because the dienes are conjugated, which means they're in electronic communication with each other. And this doesn't work if you have a polymer like this. So the DF of it, if you just look at it, you can say, oh, the DF of this this diene is 4, right? The DF of this diene is 4 because I've got 2 sets of double bonds. But because of this special conjugation, the DF of these dienes is actually only 2 because you're getting a linear polymer. So it's not an exception. You're just moving that double bond because you've only connected 1 chain end here and 1 chain end there. So this DF is 2. This DF, which means a linear polymer. If I polymerize this monomer, this is DF equals 4 because I get a chain here and a chain here. So I have 4 different chains that's connected to 1, 2, 3, 4, and I can't move any radicals around here because these are not conjugated, so I can't get any resulting double bond in the center of that chain. The radical just doesn't move that far. Yes?
What if there's another double bond between them?
Yeah, so then you have really interesting stuff. So as long as you have conjugated double bonds, you do have the possibility for this. We are not going to study those types of monomers. We're only going to study dienes that are separated by just 1 bond here. And so this is called 1,3-butadiene. This is called isoprene. And if you look very closely at isoprene, it's 1,3-butadiene with a methyl group on it. And so when we have substituents, you know that what are the organic chemistry rules of substituents? How do we number them? Yes.
There's like a priority list.
There's a priority list, but what do we want the numbers to be? Yes, we want the numbers to be low, right? So we start from the most substituted. And so we oftentimes won't have multiple substituents, we'll just have one. And so we've got 4 main carbons in our dienes. 1, 2, 3, 4. The substituent goes on the lowest numbered carbon always. So even if we turn the structure around, we just number the carbons the other way. And so we call this the 3,4 double bond. And we call this the 1,2 double bond. Notice there is no 3,4 and 1,2 in 1,3 polybutadiene because it's a symmetric monomer. But when we have an asymmetric monomer like isoprene, this is always 1, 2, 3, 4 carbons. And it turns out there's different ways to do this double bond polymerization that I'm going to tell you a bit in a sec. So you have to pay attention to the numbers because the numbers will tell you how it's polymerized. All right, let's go just a little bit further. All right, so you can look at that. Let me go here first before I ask you clicker questions. So the way this monomer works, 1, 2, 3, 4 carbons, right? If I have 1,2 addition, that means my polymer chain is just going through the 1,2 bond. That's what it's called. So the numbers tell you what carbon the polymer chain is going through. This is also called vinyl addition because it's like we're polymerizing a vinyl monomer just with 2 different substituents on it. 3,4 addition means the polymer chain just goes through the 3,4 double bond and you get a structure shown like this. Great. We will continue to review that. Cis 1,4. We've got our cis conformation. Remember, cis and trans are conformations. And so because we have restricted rotation around the double bond, we make our polymer connections. Get rid of this guy. We make our polymer connections to the 1 and 4. And so we get this diene addition that we just talked about. And then with trans 1,4, we have the trans conformation and we get 1,4 addition. And so we're connecting the polymer chain to 1 and 4. And you know what happens then? We push the double bond into the center. So in cis 1,4 and trans 1,4, this is where you're moving the double bond to the center of the molecule, right? You still have, well, I guess we have to number this way. 1, 2, 3, 4. 1, 2, 3, 4. So you have the double bond between carbons 2 and 3. When you have 1, 2, or 3, 4 addition, you just have this pendant double bond sitting there because you don't polymerize that. You don't move the double bond when you just have 1, 2, or 3, 4 addition. So this is worth writing out to practice this. Questions? All right, you can get your clickers out. So what does the 3, 4 addition product look like for this diene? Let's see, 3, 4, yeah, let me start the clicker. See if all 51 of you are still there. Okay, 3, 4 addition. My polymer chain is going through carbons 3 and 4. What is the substituent that's sticking out of that? And I just need to figure out what that looks like. So I get a carbon-carbon backbone. This is looking pretty good. This looks ugly, right? No double bond there. I know the double bond is going to be pendant. This has a pendant double bond. That's looking pretty good. This is looking okay. There's a pendant double bond there. These structures don't look very good. And so the real question is it A or C? And you can figure it out based on how things are connected to carbon 3. How many substituents does carbon 3 have connected to it? I mean, it's got a hydrogen there, right? But notice it only has one carbon-carbon bond coming out of it, right? That looks great. This has two carbon-carbon bonds coming out of carbon 2. That one's not right. Okay, make sure you ring in. So we introduced two complicated but short concepts, tacticity and dyeing addition. Both of them are going to take some practice to make sure that you have enough visualization of what these look like. That's why we're taking the extra day for review. That's why I have some extended office hours. Hold on, one more question. Yeah.
How would the numbering go?
How would the what?
The numbering. Like, say, 1,
Oh, so the numbering is set by the monomer. So once we do this, this is 1, 2, 3, 4. So if you look very closely, we just put the polymer chain through 3 and 4, and then we make sure that 2 and 1 are out where they need to be. So the connectivity stays the same. All right, thank you very much. I will see you in office hours and class on Wednesday.